Hey everybody, welcome back to the Foundations of Science class on earthquakes. As we mentioned in the syllabus, we're going to be using the 2010 Haiti earthquake as an example to show you kind of what can be done with how we understand earthquakes and the tools available so that you can think about applying some of these same tools to constrain the seismic risk in the different areas you're looking at and which ones will be most appropriate for the different areas. To refresh your memory about the 2010 Haiti earthquake, recall it was a magnitude 7.0 earthquake. Not a very big one. I mean, it was big enough to cause a lot of damage, obviously, but as far as energy release, we'll see it wasn't really all that large. Bit of a worry is that it killed somewhere between 86,000 people and 316,000 people. The fact that we don't know exactly how many people died speaks to the vulnerability of the area. Curiously, it caused about $8 billion in U.S. damages. You'll see that was a significant percentage of Haiti's overall GDP. So it's a big loss for the area, and it's also a significant amount of their GDP, which means it really packed a wallop when they had to sort out exactly how to respond to this earthquake. Okay, to get us settled in geographically, you'll see New Haven, Connecticut up there in the very north. If you go dead south from New Haven to the island of Hispaniola, Haiti occupies the western side of the island, and the Dominican Republic represents the eastern side of the island. If we zoom in on the area, you can see the complex network of faults that exists in this region. To the north of Hispaniola, you'll see the major plate boundary between the Caribbean plate to the south and the North American plate to the north. Port-au-Prince, the port itself, sits directly on the Enriquillo fault there in red, but there's also a series of much more minor faults that splay off the Enriquillo fault. The earthquake occurred right about where that star is to the west of Port-au-Prince, and if you actually carry the trace of the Enriquillo fault down through, it pops through the island of Jamaica and helps define the other port in Kingston, Jamaica. This worries me. Okay, if we look at the tectonic setting of this area, I want to show you a couple things that really make plate tectonics and thinking about movement of these rigid lithospheric plates over a plastic asthenosphere somewhat interesting. If we pin down the North American plate and only consider motion of the Caribbean plate, you can see how strain varies across the region. The overall plate direction is mostly east-northeast, but you can see the plate boundary east of Lesser Antilles starts wrapping around to the south. If we have the plate vector that's going to the northeast and a south plate boundary, that ends up being a subduction zone. If we have the same vector going on a east-west fault, it tends to be more of a strike-slip type fault. So depending on what the orientation of the fault is and the direction of the plate movement tells you exactly what kind of plate boundary we have. Another really interesting thing to notice from this image is if you see the vectors, the arrows that are pointing to the northeast, the vectors represent both length and direction of movement of the plates. The southern part of Hispaniola is moving more than the northern part. That tells us that plate boundary is locked, or it's accumulating strain on the septentrional fault to the north. That poses bad for Santiago in the north, as well as it does for northern Haiti. As more strain accumulates on that, it's more likely to have an earthquake. Okay, if we look at the 2010 earthquake, we want to figure out how big it is. We can start thinking about the earthquake magnitude, which we talked about last time. The size of the earthquake is related to the length of the fault. In this case, it was about 40 kilometers long. How fast the plates slide past each other in this area is about 2 centimeters per year. And how long since the last one. Now this is where it gets kind of interesting because the length of time between earthquakes can vary. It's not always exactly the same. And depending on how much strain has accumulated the time since the last earthquake will tell you how big the next one will be. So let's go back into the books and figure out when the last earthquake was in this area. If we look into earthquake history of Hispaniola, you can tell it's had a very busy earthquake history. Records started in the early part of the 17th century and continued on through the present day. The last big earthquake that occurred around Port-au-Prince was in 1770 on the Enriquillo fault, we think, which is about the same length of fault that ruptured in the 2010 earthquake. You can see some really big earthquakes up by the Septentrional fault in 1946 and 1842. Those are much more damaging earthquakes, as was the 1751 earthquake in the southern part of the Dominican Republic. The 1751 earthquake that hit Port-au-Prince actually destroyed Port-au-Prince, and they said, we're not going to rebuild. Well, they actually went ahead and rebuilt. 1761 came along, caused a lot of damage in Port-au-Prince. They said, we're not going to rebuild again. And then they did. And then 1770 came along, they said, we're definitely not going to rebuild again. They did. And then it took them the next, 200 and odd years to actually get to a point where we are now in 2010, and the last earthquake happened. How much strain accumulated in the 200 odd years? It's up to you to figure out. Okay, one thing that's really important is to get an idea of the size of these earthquakes and something that people can wrap their brains around. So how big was this earthquake? This earthquake released enough energy to power the island of Manhattan for an entire year. That's a lot of energy, obviously. More disturbingly, perhaps, though, is the 2004 Indian Ocean earthquake, which is the largest earthquake recorded recently, was about 2,000 times more powerful. That was a really, really, really big earthquake. One thing I mentioned before is this network of faults is the one thing that gives Port-au-Prince its economically important location. It's also what causes the damage. So you can see this crisscrossing network of faults actually defines the bay, which is why Port-au-Prince is there, why it's actually a port. So people chose to live here because of the economic activity it can bring. But nice safe harbor in there. This area gets hit by tropical cyclones just about every year. So if the tropical cyclones are coming in from the east side, they're really not going to have much punch left by the time it gets to this almost perfect safe harbor in Port-au-Prince. I want to compare this area to another bay area. San Francisco Bay is also another bay that's safe harbor that's defined by faults. The San Andreas, the fault to the south, defines the southern and western part of the bay, and the Hayward-Calaveras system to the east defines the other side of the bay. In 1989, there's a large magnitude 7.1 earthquake that hit in the Santa Cruz Mountains. It's called the Loma Prieta earthquake, and people were worried that it was actually on the San Andreas fault. San Andreas fault prior to this had ruptured in 1906 in a very large earthquake that did a lot of damage in San Francisco. This earthquake also caused damage in San Francisco, as you can tell from the picture in the Marina District on the left-hand side of the screen. Curiously, the Marina District is formed in the north part of San Francisco, is actually built on the rubble that was bulldozed into San Francisco Bay from the 1906 earthquake. When this earthquake happened in 1989, because the ground wasn't very solid, wasn't very well compacted, it actually liquefied, actually turned into liquid, and the foundations of the building just sunk into the ground in 1989 from this relatively low magnitude earthquake. If we do a comparison between San Francisco Bay and Port-au-Prince, these are actually at the same scale. I just rotated Port-au-Prince 90 degrees so you get an idea of how similar these two areas are. You can see the faults that define these bays, and you compare these two earthquakes. Loma Prieta was a little bit bigger, magnitude 7.1 versus a magnitude 7 earthquake in Haiti. In the San Francisco Bay Area, 7.4 million people were exposed to strong shaking during the Loma Prieta earthquake. The entire population of Haiti is about 10 million, give or take, and of that 10 million, 2 or 3 million are in the capital city of Port-au-Prince. The population density, however, is really a lot different. In San Francisco proper, in the city of San Francisco, that's the highest population density I could find, there's about almost 7,000 people per square kilometer, compared to Port-au-Prince, where we have 28,000 people per square kilometer in the city. That's some of the highest population density in the world. The real difference here was in the death toll. During the 1989 earthquake in San Francisco, 63 people died, which is a lot, make no mistake, compared to the around 200,000 people that died in Haiti. The gross domestic product of the Bay Area itself is estimated in 1989 dollars to be about $300 billion with a B dollars. And in Haiti, the entire GDP of Haiti was actually $11 billion in 2010 when this earthquake hit. I found that number higher than I expected because Haiti is a really impoverished country. However, that's the number that the World Bank offered at the time. And to give you an idea of vulnerability, in San Francisco proper, just the city of San Francisco, there are 42 fire stations. So think about emergency response compared to 2 fire stations in all of Haiti, and how active those fire stations are is a different story. What we're going to be doing this week is reading a paper by Eric Calais. He's a Frenchman who was working at Purdue University at the time of the earthquake, and he's done a lot of work in Haiti. He speaks the language. Haiti is a French-speaking country still. They actually speak a language called Creole, and Eric actually speaks Creole quite well. He's been working down there for years. And he did a lot of the follow-up work on this event based on data he'd been collecting for years prior to this earthquake. It was his student who wrote the paper that we were going to read on this one, but I looked over the paper again. It really is just too hard to understand. So we're going to give that paper a miss, but read Eric's paper instead. Eric's paper talks about several different ways of measuring the hazard of this fault, and I want to go and explain these a little bit so that when you read the paper you'll have an understanding of what we're talking about. One of those methods to measure elastic strain accumulation. Remember we talked about how if we have two plates that are stuck together, locked together, and they're moving, eventually they're accumulating strain, and when the strength of the rock is compromised, boom, they rupture, and that's an earthquake. One really effective way of measuring elastic strain accumulation is using global positioning systems. You can put a GPS unit on either side of the fault and measure how fast they're moving compared to the lack of movement actually right on the fault to get an idea of how much strain is accumulated. And after an earthquake, there's a really complicated, complex method called radar interferometry, which can tell you how much displacement has occurred along a fault, how much the ground has deformed afterwards, which gave us a really interesting result. As you can see from the title of this paper, that Eric Calais believes that the rupture of this earthquake occurred not on the major Enriquillo fault, but rather on an unmapped fault that was recently, until this event, undiscovered. This has implications for future risk on the Enriquillo fault.